Now the concept of this coordinate system transform like that, we define a four vector, so-called four vector, and this is the what we call the position four vector, position of time. It's our space-time four vector. So a four vector like that is now you have x0, which is I'm using language later, but let's just keep it before we introduce the tensor index notation. Just you have CT and then you have a spatial vector that's combining the time and space. You get this four vector, and the property of this four vector is now that from the derivation of the Lorentz transformation, we know that the norm of this one is c squared t squared minus x squared, and that is invariant, and I suggest we do it. Anyways, so this is after you take the norm. This is scalar. What a scalar means later on define that is unchanged with respect to reference frame. Whatever reference frame you measure a scalar is still the same value. So that should be the norm of a four vector should be a scalar. And likewise, if you have two four vectors, so you have A, so you have A0 and A vector. And next one you have B0, B vector. Then you can define a dot product B dot B with AC and BC. Actually, minus the usual dot product, usual space, three-dimensional space dot product. So, and this should also be a scalar. So we define this now for later convenience. So just remember that these are scalars. So later on, we'll actually say we have one four vector we define, and then it's satisfied with another quantity b that it satisfies is something like a dot product, and that is invariant. Then you can conclude that the b also is a form for vector. So something like if a dot b is 0, then you know that if you know a is a four vector, b will also be a four vector. And one direct example is that we already mentioned that a phase of a wave is invariant, because phase is just measuring how the wave moving up and down, and that is just an absolute count that should be invariant with respect to frame. So the phase we define, like when we measure in the wave chapter, we know that is omega t minus k dot x, right? Now we know CT and X form a four vector, so write omega CT and divided by C minus K dot. So CT and X they form a four vector here. So you know that by this property, this is a scalar because this is independent of frame. So we know that this omega C and K also form a four vector. Right. This is the what we can give a name like frequency wave number four vector. Okay. So that's one direct application. Okay, up to here. Okay, this is up to here, just language. Now we
So what is the use of writing for
we'll talk even more about that. We'll actually later on introduce tensor notation. I know some of you haven't taken math physics, but it's just like a preview for you. We'll use some language of tensor notation, introduce 4-vector tensor notation and four vector, 4 tensor. And the reason is that we want to write the Maxwell equation invariant form when you can express your physical law or physical equation of nature in 4 tensor form. Then you make sure that it is consistent with special relativity. It means that it's invariant. The form is invariant with respect to frame, which is important. Just like the point in the physical space, it should not depend on how you choose your coordinate system. Whatever you rotate your coordinate system, it should not change. So whatever the physical description should not depend on the frame. Therefore, it's important to write equation or physical law, express physical law in invariant form. And to do that, it's kind of unavoidable. You need to use some kind of language, the tensor notation. Otherwise, it's not apparent. It's very not apparent. Like the original Maxwell equation, you cannot see right away it is invariant. But after later on, hopefully this week, Wednesday or so, we'll express all the 4 Maxwell equation in tensor form. Then you make sure that the Maxwell equation is totally invariant with respect to special relativity anyway. And later on, I mean, this is like a nice mathematical feature, but you may say it's not essential. But later, if you want to further generalize to general relativity, or what we actually means is including effect of gravity, then the tensor notation becomes unavoidable. There's almost no other language you can use to express general relativity, that kind of thing. Okay, so the language actually should help you to develop your theory, right? Because you can have all the great concepts like Einstein, but if you figure out all the things like so-called equivalent principle, we thought about that for a long time. We invented all this discussion of elevator and all that, and we figured all that, but it still took him 10 years to do that. General relativity from special relativity. And the major obstacle is finding a right mathematical language to express that. You can have all the right concept, but you don't know how to write it down. And you need the right language to do that. Those languages are borrowed from the discussion of geometry, the Riemann geometry. And Einstein was not a mathematician, so it took him a while to figure out all this math or all this notation, get the math right, get the language right to get the general relativity. The tensor notation is almost unavoidable in general relativity. For special relativity, it's a good thing. It's a nice thing. It's make the form much nicer, but may not be essential. Okay. Now the next subsection is talk about this space-time events, and we do a little bit classification. So you have like now draw it not like that. This is like what we call the space-time diagram. Okay, so this is the time axis is z-axis, the light cone is a diagonal line, c to ct equals to c. Wait, it's not. And events are absolute things, so you have like the 2 events, you have x1 in terms of 4 vectors, so this is or ct1, x1, or c1. I mean, actually, it's actually useful. Use vectors, so just x1 vector. I mean, this is just a representative. This is not just one coordinate. And we have another point. It depends on where it is. So another CT2, X2, right? And by the fact that all this event described by these coordinates are 4-vector, the difference between two events are also 4-vectors. And the norm of 4-vectors are invariant. So you can subtract the two and take the norm. So you have c squared k1 minus k2 squared. It is the difference, and then take the norm, and then you have x1 minus x2. So it's invariant, which means this is the same as measured in another frame. So you imagine that you can do a transformation, Lorentz transformation to another frame. So we already talked about that. If you change the other frame, so this is the CT point, C point, right? It should be the same, minus 1 point minus 2 point. Okay, and then this is, I think they can call it delta. S12, this is S12. This is just the norm of difference between two events. This is what we call event. An event is an absolute thing. The coordinates are your choice. You choose whatever, how you basically what frame you measure to express an event. But the events are absolute, so that the norm is the same when you express in different frame. Okay, but then we classify these things according to whether this is positive or negative, right? And if this is positive, which means this difference is greater than this one, so this event is not here. This is separated by a light beam. Then this event probably will be something here. X2. This is event 1. The event 2 would be something like here. And because the difference in t, which is this difference, is greater than the difference in x, or in the space, right? And it also means so this is what we call a time-like event. If S12 is greater than 0, it's called time-like. There's a description. Time-like, this that's called time-like separation. Or if this greater than 0, these two events are time-like. Right? So greater than 0 is time-like. What it means is that you can find a transformation or a k-prime frame such that these two events are at the same. Let's just say this actually should be over. It should be even more. The slope of these two events should be greater than 45 degrees. So 2 should be here. You should find you can find a frame such that the two events are at the same location or the same coordinates. You can find a frame going through this, then which means you can find a frame, k-prime frame such that the spatial difference is 0. So only have time difference in this frame. And obviously, this you define like that. This is positive. Okay, and likewise, if this less than 0, this is space. Right? And obviously, that is a 1, 2 in here, so 1, 2, so 1, 2 would be like here. And if it's less than 0, then you cannot find a frame so that it occurs at the same location, but you can find it a frame such that they occur at the same time. So you basically choose your frame such that these two, the time axis is going through these 2 points. And then like t prime will be 0, you only have x prime, x1 minus x2 prime, right? So that's space like. Okay, so that this is this is just classification, but we can discuss two famous consequence of this transformation. So for say so for two particles like and so if you occur for the space-like event, if you occur at the same location, say if you're a particle, and we actually consider some kind of arbitrary motion. So get into complicated figures, I think so. So like discuss say some point or particle moving relative to the K-frame with some velocity. This velocity doesn't have to be constant, it can be arbitrary, but because it's velocity, the slope must not be less than 45 degrees, because otherwise the speed will be greater than the speed of light. So you cannot do that. So, so something like that, you can arbitrary. So you have some velocity as a function of t, right? But if you have, say, because not just a particle, if it's like a spaceship or something like that, you follow this. If you can follow this object, you stay with this object and you measure the time, and instantaneously you can define two events. So you have a two event, not necessarily a straight line, but some two events. Then you can have a delta S here. This is this becomes instead of S12 is delta S between these two instantaneously moving events, between these two interval. Then if you stay with this object, obviously you're at the same location with respect to your own frame. So this space difference is 0. So what you measure here becomes what we call the papa time. If you follow the object, then you stay with that object, or even though you are moving with arbitrary velocity, then the time, or you are wearing a watch, whatever the time showing on your watch is what we call the papa time. And so to consider delta S, right? Delta S, c squared, delta t squared. In the original frame is delta t squared minus delta x squared. But then this in this frame, this time is called the propaganda of c squared tau squared, or delta tau squared. Change of propaganda. And so, but within this little instant, delta x moving in the velocity v, this v in the k frame. So delta x is v squared delta t squared. So c squared minus v squared delta t squared. And then from this, you compare this divided by c, and here this implies that the change of the proper time, or you can say d tau, is dt, and this is pull out the c squared becomes 1 minus v squared over c squared, 1 minus beta squared, which is 1 over gamma squared. So d tau is related to dt. Okay, the gamma is always greater than 1. You don't really erase that. Beta is always less than 1. So this, the whole denominator is always less than 1, so gamma is always greater than 1. So gamma is greater than 1, so 1 over gamma is less than 1. So it means that d tau is always less than dt. So this is less than dt. And so that is called time dilation. So it means that whenever you move, your clock moves slower, move against the another frame, another reference frame. So in that reference frame, you measure your time difference. But then as you move, you're carrying a watch. The watch will move slower whenever you move. Okay, and that is the basis of the so-called twin paradox. So it means that you are going on a loop. So going somewhere and then come back. So if you're going along this trajectory, space-time trajectory, then the time it takes as you measure yourself when you carry moving, your own watch is showing less than the actual time difference between these two events. All right, so that means that the twins that are going on this on a trip, going somewhere and coming back is age less than the twins staying behind. So that's the twins paradox. Although there's complication because I already asked you, the Earth is not a true, uh, not a true inertial frame, so that is complicated. The twin paradox, you need to state that the twin actually staying behind should be in the inertial frame. In our case, the Earth is not exact inertial frame, so that's a complication, right? So that's asymmetry between the two. This is an inertial frame. The K frame is an inertial frame, but as this uh, object, the other twin going on this curve relative to K, then this is not an inertial frame. So therefore, there's a time asymmetry that the twin that going on the non-inertial frame, the proper time it shows becomes less than the time in the inertial frame. Okay, this is coming from all this. So this is the relationship, right? This is the time dilation. It's okay. This concept. Well, there's sometimes I don't know whether people ask you to explain this kind of thing. People ask whether you can give a good explanation. Well, so that's time dilation. That is actually easier than the space, so-called space contraction. And the concept of space contraction is a little bit more complicated because it depends on operation, what you mean by the measurement in the two frames. Basically, the idea is that if you have a frame moving, say like the K prime frame moving relative to K with a certain velocity, forget about this. Yeah. This is your CT point. This becomes your D point. Okay. What the contraction means originally in the CB prime and the K prime frame, you have some kind of distance like a ruler. So you start at the origins. C prime is 0 to a certain point. C prime is L or something like that. So you have a ruler that, I mean, if you measure in K prime frame, which means that the ruler is in the rest frame of the K prime frame, that it has a length L. The space contraction is saying that if you measure this ruler at the same time in the K frame, what is the length? So that's it's operational statement. You need to measure this ruler at the same time in T, which obviously is not these two events because these two events T is different. Obviously, T is different. This already moved. So you need to trace it back to a time in the K-frame, chase this point, the other endpoint, the endpoint at the origin stay at t equals 0. The endpoint at L, you need to trace it back to a little bit in time to the same. This is assumed to be initial time, so this is t is 0, right? And then this lane is your the measurement of this lane in the original frame, in the K frame, I should say. Okay, and so by this operation, what it means is that you want to choose t to 0. You want to choose this difference to 0. Basically, set that to 0. And you measure this one, this length, or the length square between this point, these 2 points, right? But this 2 point is at the same time in t, so you need to figure out the difference between these two. I should say this should be a difference. Right. The idea is to use the Lorentz transformation, but use it the inverse one, because the inverse one is like setting beta minus beta, so CT. Now it's gamma beta instead, minus gamma beta. Right. You want this to fix time to 0 or t to 0 or the delta t. You change. If this is the delta, you can actually change it again. Right. You want delta t to be 0, so that you know that if delta t is 0, then these two are related to each other. So you have c delta t gamma, c delta t minus beta delta c prime. That's equal to 0. So delta c, this is delta c prime. The delta c prime, or delta c prime square is equals to c square. Delta t prime square divided by beta. Right? So this is equal to this 2, but then what I should actually say delta t prime, because I want to express this in the t. So delta t prime is beta square times delta t square. So this is delta t prime square is beta square, so c square, beta square, and minus 1 times delta x square. Okay, and there's a minus sign. Let's say this delta L. We write it, so delta L square is reversed as delta L prime square. And this is 1 minus beta, which is gamma square. Whatever, you take the square root, is like delta L is delta prime divided. Okay, so gamma is greater than 1, so less than. This is less than 1 over gamma, less than 1. So delta L is less than delta L. That is the space contraction. So whatever the ruler, you measure in this way at the same time in the K frame, then the length appear to be smaller, shorter. Okay, so that is the so-called length contraction. All right, so those are famous Weierstrass effect. Okay. Part D. Any question up to here? So we finish up to, I think, finish up to part C. Okay, part D. If Doppler effect, we already learned about we already talked about this frequency space, frequency and space for vectors. So therefore they transform also like four vectors, so we can write down the transformation so that you could figure out the Doppler effect. So like omega prime, this is omega prime with C, and then let's see, actually using K parallel, K parallel, K parallel is along the direction of relative velocity. So this is prime. It's the same gamma minus gamma. They transform like the space-time, so transform like using Lorentz transformations. Omega over C, K parallel. And then the perpendicular component doesn't change. Okay. Then depends on what you want to calculate. Like if you want to calculate omega prime, just the frequency as measured in omega prime given the frequency in omega, then just the first equation. Omega C goes down. Omega over C minus right. To get the Doppler effect, obviously, what you only need to do is dispersion relation, because you have the frequency here, you have a wave number here. You need the relationship between wave number and the frequency, and uh, the wave factor, of course, the dispersion relation is simple, at least for vacuum. Just K is omega over C. Right. Then K parallel, it depends on how you observe it. So if you have you propagate. So this is a propagation velocity according to the special relativity V. So this is the V direction, but the K is making a direction with a certain angle, right? Then K parallel means it's parallel to the velocity, relative velocity between the two frames. So this is K parallel. The K parallel is K cosine theta, and K is omega over C. So omega cosine theta over C. Okay, so you can substitute this into here. So both now have omega over C. So omega over C and 1 minus theta cosine theta. Okay, so that's the Doppler effect 11.30. So it depends on what the angle. So obviously, the extreme cases is whether theta is 0 or pi. Theta is 0, it means it's propagating with respect to towards the K prime frame. So this velocity is K prime moving relative to K. Right? If you have if in the K frame you have omega, then K prime frame, if you are moving away from the source, then you receive wave, then theta will be 0. And so the frequency you observe in the K prime frame would be 1 minus theta, which is smaller than 1. So it means omega, the frequency omega will be, actually I need to consider this gamma. So this is, the theta is 0. Let's see, I should write theta is 0. This omega over C, 1 minus theta. This is square root 1 minus theta square, which is omega over C. Square root of 1 minus theta, 1 plus beta. Okay, 1 plus beta is greater than 1. 1 minus beta is less than, but 1 over 1 plus beta is less than 1. So the whole thing is less than 1. So less than omega over C. Okay, so when you move away from your source and the wave is propagating towards you, then you get this decrease in frequency. So that's called a redshift. Okay, and so likewise, if you're doing it another way, uh, then if you increase the frequency, that's a blue shift. And so that how you consider Doppler effect. And this is valid. This is totally relativistic. And sometimes people will use non-relativistic consideration. May like if you're not considering the electromagnetic wave, you not consider light, you can consider sound wave, and the formula will be slightly different because you're not using this, especially the dispersion relation. If not electromagnetic wave, the dispersion relation will change. You need to be a little careful. But these formula is just for electromagnetic waves.